about carboxylic acids and their derivatives, and right at the end of the last lecture, I pointed out that if you have a nitrile, which is a compound of this type, you can boil it up with this acid and you will get a carboxylic acid. And I went through the mechanism, and some of you were moaning and groaning. You've never seen such a complex mechanism in your lives before. I will later today go through the mechanism again, because there are two ways of hydrolyzing a nitrile to an acid. Now, what I want to do next, though, before going through that mechanism, is I want to show you how you can use this type of information. Just supposing that you wanted this substance. You have to make that substance, supposing you could not buy it. So what do? Well, you can look at it and say, oh my God, I don't know. You can break down and cry and give up. But that's not acceptable. You're being paid to make this substance. So you look at it, you see it's an alcohol, it's also an acid. So you can ask yourself, do I know any ways of making alcohols? And do I know any ways of making acids? And the answer hopefully will be yes in both cases. And so in your mind, or on a bit of rough paper, you need to jot down the various ways of making alcohols and the various ways of making acids. And then for each of those ways, you ask yourself, is this way likely to be applicable to this problem? Now, since I'm dealing with acids, I'm only going to tell you how to make this compound on the basis of what you know about making acids. Now, what you know about making acids is one of the ways is to hydrolyze a nitrile. So this baby could clearly be expected to be the product of hydrolysis of a nitrile. And so now you have changed the problem of making the acid into a problem of making this hydroxynitrile. And so once you realize that, you go down to the stockroom and you see if they've got that nitrile there. And you find they haven't got it, so you'll curse a little bit, you go back to your lab and you'll say, well, how can I make this nitrile? And you know how to make nitriles. One of the ways is to displace some leading group with cyanide ion, because by an SN2 process, you could convert that chloroalcohol into the nitrile, then hydrolyze the nitrile and get the acid. So you go down to the stockroom again, you find out if they've got that. You find, yeah, they've got a liter of it. So that's great. So you take the stuff, you rush back to the lab, you set up the experiment, and then when you come back in the morning, you work it up and you isolate this. And by that time it's lunchtime, you set up a hydrolysis. You go to the cafeteria, have a quick sandwich. By the time you come back, you've got your acid. So that's just great. So this is how you analyze how to make something. You look at various features and you ask yourself, do I know how to assemble something with that particular feature in it? Now this actually may seem complicated to you. It's actually a very simple one. When you have a complicated target molecule, it becomes infinitely more difficult. But don't worry about that. That's not part of this course. Now, there is another way of making carboxylic acids besides, or there are several ways, of course, besides hydrolyzing a nitrile. And one of them is using your old friend, the Grignard reagent. If you take a Grignard reagent, which I'm going to write in this way, and you treat it with carbon dioxide, which I'm going to write like that instead of write CO2, I can actually draw it, you know, or you can certainly understand, that what's going to happen is what I'm writing on the board, and then if you treat that with dilute HCl, you will then get the carboxylic acid. And all that's happened is that the Grignard reagent, R minus, which could be Me minus or Et minus or cyclohexyl carbanion or butyl carbanion, it's just acting as a nucleophile that's attacking a carbonyl group. Because carbon dioxide is in fact a substance that's got a sort of carbonyl group. And you now have numerous examples in which I've shown you something with pair of electrons attacking a carbonyl carbon. And so this is yet another way of making a carboxylic acid. You allow the Grignard reagent to attack carbon dioxide. And one of the easy ways of doing it is to take some solid carbon dioxide, so-called dry ice, put it in a flask, and squirt the Grignard reagent on it. Fizzing and so on, and then you stir with dilute HCl, you can get out that compound. And of course, I've shown here the group R, but you can make a Grignard reagent from an aromatic halide. This, of course, is the very simplest one. I'm going to write it like this. And if you treat that with CO2, you will get benzoic acid after acid workup. So that's a very convenient way of making carboxylic acids. And what you should do to check that you understand all this is to do problem 17.5, which is the same as problem 18.6 in the 9th edition, and you should do 17.6, which is the same as 18.7 in the 9th edition. Now, I want to talk about a slightly different subject. And what I want to talk about is, I'll write it down because the name is a little bit intimidating, nucleophilic addition to, and what's the exact words of the book? An acyl compound. And what I mean by that is that I've got an acyl group, which is carbon attached to a carbonyl. So an acyl group is this bit that I'm circling in red, and then it's attached to some group X that is a leaving group. Now, let me just backtrack for a moment. Obviously, I've been talking in this lecture and in the previous lecture about acids and their derivatives, and all of those compounds, here's an acid, but all of them have that bit in it, and the acid has OH, an acid chloride has Cl, an acid anhydride has another acyl group attached here, an amide has nitrogen here, and the nitrile looks a bit different, but it is at the same oxidation level as an acid, because the acid, this carbon, is attached by 3 bonds to heteroatoms, And in a nitrile, the nitrile carbon is attached by 3 bonds to a heteroatom. So nitrile and acid are the same oxidation level. So I'm talking about acids, and therefore talking about substances like this is really part of that subject. Now the question is, what should X be, and what happens when a nucleophile attacks that species? Now from everything I've told you this a zillion times, you're probably getting sick and tired of it. Carbonyl groups polarized in such a way that there's a build-up of electron density on carbonyl oxygen, slight deficit of electron density on carbonyl carbon. So if anything's got electrons that he wants to attack something, and you expose it to something with the carbonyl carbon, a very likely place for attack is at the carbonyl carbon. I mean, basically, a carbonyl carbon, in most cases, is screaming out, nucleophile, attack me. That's what it's doing. Now let's have a look and see what happens for various types of leaving groups. In order to do that, I need to clean the board. Somebody has got to invent a method whereby the board is sort of cleans itself automatically by the press of a button or something like that. Because I'd much rather go to the gym and have a workout than clean the board this way.
Also, do you slide the thing? Oh, yeah. And then it just erases it?
Along the bottom.
Yeah. Oh. So if you had like a button like that where it just like erasers or stuff on it, and then it just sweeps that one word.
Okay,
one line.
Somebody else like make an investment.
Stop something?
I lost my mustache.
Her back.
It fell off. I don't know where it
This
went.
is an acid chloride. If you go to the stockroom, you can get a substance like this. It's called acetyl chloride. And it's just a simple example of the compound class called acid chlorides. Now, the nucleophile that I'm going to use is going to be water. Here is water, and what happens is it attacks the carbonyl carbon. And then, this isn't quite what the book says. I don't like the book. You get proton exchange, in other words, a proton from here gets onto here, either from the same molecule or from some other molecule, and now an electron pushes on the lone pair, pushes out the chlorine, which is a good leaving group. So you can see what has happened. We have hydrolyzed an acid chloride. So if you make an acid chloride ever, and you use it in a reaction for combination with some other compound, you better protect it from water, because water will attack the carbonyl group in the way that I've shown, and you'll end up with the acid. Whereas what you really want is to keep the acid chloride so that it can react with the organic molecule that you're using. And you'll see in a moment some other reactions of acid chlorides. Now, is an acid chloride the only acyl derivative that undergoes this process? The answer is no. All that you need is that group X, where here it is chlorine. All you need is that group X to be a leaving group. And another type of species, I'm going to write down acid chloride first. So that's the leaving group. There's another one that's a little less reactive. That's an anhydride, because if some nucleophile goes in there, the electrons come there and then come back, this can come out, because it's a leaving group. It's not a good leaving group, but it is a leaving group. So an acid chloride is more reactive in that respect than an ester. And if you have an ester, and you have a nucleophile can attack there. So what I've shown you in the last few minutes is that if you have an acyl group, which is just this bit, attached to a leaving group, which is very frequently chlorine, or in the case of an anhydride, it's another acyl group on oxygen. And in the case of an ester, which is the worst of these, it's the least reactive, it's OR, where R is methyl, methyl, propyl, cyclohexyl, butyl, whatever you like. If you have such a compound and you treat it with a nucleophile, the nucleophile will attack the carbonyl carbon, the electrons will move on to the oxygen, then they'll come back, expel the leaving group. So what you've actually done is you have exchanged the leaving group for something else that comes from the nucleophile. And you will see later today what sort of things you can exchange the leaving group for. But first of all, I'd better tell you how to make acid chlorides, because they are the best. They're the most reactive of these acyl derivatives that come from acids and that can be used to transfer an acyl group onto a nucleophile.
He just started writing.
This little white pen has muscle. I fell off the bag. That's so funny. It fell into that bag.
She told me she would be late, but I didn't.
If you take a carboxylic acid and you treat it with this stuff, SOCl2, and the structure of that is this, and this is called thionyl chloride. You get the acid chloride. And if you haven't got thionyl chloride, you can use phosphorus trichloride. If you haven't got phosphorus trichloride, you can use phosphorus pentachloride. Now the mechanism of this is fairly straightforward to write something that's plausible, but I'm not going to give it to you because I don't think you like these mechanisms with loads and loads of arrows, since when I wrote one up for the hydrolysis of a nitrile, there were moans and groans from the audience. And you don't have to know it for this particular case. But this is the way of making acid chlorides. Now, I want to show you what sort of things you can make from an acid chloride by using this business that I just described, in which you allow a nucleophile to attack the carbonyl carbon and replace the chlorine. So let's have a look and see what happens. If you treat that with the sodium salt of an acid, then this O- will act as a nucleophile. And that nucleophile, that O- will come in here, push electrons onto oxygen, the electrons will come out and push out the chlorine, exactly as I described a few minutes ago. So the actual product that you get is the anhydride. If instead of that you use an alcohol and a base, and frequently the base will be pyridine, well, once again, the oxygen will attack the carbonyl carbon, push the electrons onto the oxygen, they will come back, displace the chlorine, so you end up with an ester. And finally, well, I'll have to write it here, if you have an amine, exactly the same thing will happen, and you now end up with an amide. Amide, anhydride, and ester. Now you will remember, I hope, that quite early on when I started to talk about carboxylic acids and their derivatives, I mentioned things like acid chlorides, anhydrides, esters, amides. They're all related. You can see how they're related because you can make many of them from some of the others. You can make many of them from starting from acids. And so this business of taking an acylating agent, a reagent that takes an acyl group and transfers it to a nucleophile, by this general principle of having a nucleophile attack carbonyl, and that's ultimately followed by expulsion of the leading group, you can use that to make all sorts of things, esters, anhydrides, amides, and other things as well. Now, I want to tell you a little, I just told you a little bit about how to make acid chlorides. I want to tell you a little bit about how to make where? Oh, yes. By a slip of the pen. Are you happy, sir? That's good. I know everybody's happy. So I'm happy. Okay, I've told you a little bit about how to make acid chlorides. I want to tell you now a little bit more about how to make esters. I've given you one way, but I want to give you another way of making esters.
So comfy.
It is, really is. My God. I don't feel like, outside, I don't feel anything, like no cold around here, but like obviously everywhere else I'm like.
Sure, you can find another massage pen really easily because it's small.
Use this for
For what?
For smoking. So then if you want another one.
I'm going to my brother's favorite ball game.
No, I want like the
They're playing Ainley.
Oh, that's what I meant.
Like the one that's I don't think I heard top teams in Canada.
I like how Joy's laughing. Just kidding.
No,
They play tomorrow.
Just kidding.
I should actually take that off the list. I think I'm getting my own. I'm getting someone online to make me one.
Are you gonna make it like a mustache?
No, you guys will see once I get it.
I've written up a particular example. If you take a carboxylic acid, and I just wrote up one particular example, propanoic acid, and you mix it with an alcohol, again I just chose a simple example, methanol. Must be very careful with methanol, it's not quite the same as ethanol. Ethanol you can drink in moderation, methanol will kill you. The other stuff will kill you if you drink enough, but methanol will kill you in a small amount. If you treat the acid with an alcohol, in the presence of a strong mineral acid, a drop of sulfuric acid, for example, or a little bit of HCl gas, you will get the ester. Now, there's a lot of questions involved in this reaction. It took a lot of very nice scientific work to find out what's going on. You see, this oxygen here, is it the same as that oxygen? Or this oxygen here, is it the same as that oxygen? So what's going on? Where are the various parts of this coming from? Obviously, this carbon and that carbon, or that carbon and that carbon. But the rest of it's not so straightforward, and I will just tell you what the answer is. And you can actually work out what the answer is going to be from everything that I told you. At least you'll be able to follow it very easily. What I'm going to do is I'm going to take the acid, and as you know from what I've written over there, I'm going to put it in the presence of a strong mineral acid. Now, strong mineral acid provides protons, and protons love to be attacked by anything that's got a pair of electrons. Well, are there any parts of this molecule that have pairs of electrons? The answer is it. Jolly well are. This baby's got some and this baby's got some. And so both of those parts will be protonated. But it turns out that only one of them is productive. In other words, only one of those sites, when it's protonated, leads on to product. If the other site is protonated, which it is, nothing happens. The proton then comes off. So I'm going to write up now the site that is protonated. And you can realize immediately that I could write a resonance structure. Now, obviously, one doesn't have to be as clever as Einstein to realize that if methanol is present, it's going to do what I'm writing up now. It's going to do that. And all these things are reversible. Now this thing here could do all sorts of things. The lone pair from this oxygen or from that oxygen could simply come back, regenerate a carbon here and push this out. That's fine, go back to starting material. You wouldn't tell them, you wouldn't notice it. You just look at the reaction, perhaps you're following it by some physical method, and you come back after supper and you take out a sample and make some measurement and say, holy smokes, it hasn't gone. But there's another process that can happen. This can lose a proton. Supposing we've got methanol in there, you can pick that up. And so now we are at this stage. And it's all reversible. And now we've still got acid there. So we've still got protons. And as I've indicated, protons love to be attacked by anything that's got a pair of electrons. And this obviously has pairs of electrons on here, on here, on here. And all of them are in fact protonated. But two of them lead on to a product. It doesn't matter which of these I deal with. Put a proton there. Now, one of these oxygens has been converted into a very good leaving group. Here is your ester. And so you can see where the oxygen attached to the alkyl group of the ester, where that oxygen comes from. It comes from the alcohol. Doesn't come from the acid. And one of the ways in which that was proven was to use some isotopes. If you start with an alcohol that's got O18 in it instead of O16, and then you make an ester, you find that the oxygen that was O18 in the alcohol is now in the ester at this position. And if you start with an acid that's got O18 here and here, because if you put O18 here, it ends up there as well, for the simple reason, that's, some of you don't follow that. Supposing I've got O18 there, now the O18's in the carbonyl group, because this acid could be protonated by another molecule of acid on this oxygen. And so if you take an O18 labeled acid, the distribution of O18 will tell you in the ester that there's no O18 here. So those are sorts of experiments establish just how an ester is formed. Now, you'll notice something. I said all these steps are reversible. And if they're reversible, that means that when equilibrium is reached, you'll have some starting materials and some product. But when you do a reaction, that's not what you want. You want everything to go over to the product. You want 100% yield. So how can you make all these reversible steps go over to the product? What you do is you use an excess of one of the components. And the alcohol, if you use that in excess, it drives the equilibrium over almost completely to the side of the product. And then once equilibrium has been reached, you know there's the law of mass action, discovered in Europe, which tells you the concentration of the starting material times the concentration of the other starting material is equal to the concentration of the various products. And if you make the concentration on the left-hand side big, then the concentration of the other component of the starting materials has to be small, which means it's all converted into the product. So you use an excess of alcohol to drive everything over. When the reaction has reached equilibrium, which, if you've done it properly, means that 99% of the starting material has been converted into this, you add a little bit of a mild base, like potassium carbonate, to neutralize the acid, stops the equilibrium, and then you can isolate what you want. The other thing that you notice is that because all these are equilibria, you can actually drive the reaction the other way. And I will probably show you later on how to hydrolyze an ester. I showed you last time how to hydrolyze a nitrile. I'll later show you how to hydrolyze an ester. Now, the other way of making esters is what I gave you 10 minutes ago. I told you take an acid chloride, you treat it with an alcohol, you will get an ester. So I'm not going to go over that. But what I will do is to show you an example. It's a little bit more complicated than what I've shown you so far.
I wish this was just a guy. Like if someone puts clothes, like you still have to fix it. And don't get on money. Whoever has them. These counts are right.
Now what's gone on here? You remember that a little while ago I said that if you take an acid chloride and treat it with an alcohol, you get an ester. And I also said that acid chlorides are not the only substances that can deliver an acyl group to a nucleophile. And the other types of substance, one of the other types of substance that can do that is an anhydride. Well, this thing here is an anhydride. It happens to be a cyclic anhydride, but still an anhydride. And so the alcohol, this oxygen, can attack this carbonyl carbon, or that one, by symmetry they're the same. It's going to attack here, the electrons will go on to this oxygen, come back and now expel the other part of the anhydride. And if you follow that through, this is what you get. So you get a monoester of a dicarboxylic acid. So that's a little bit more complicated than the simple examples that I've given you so far. Now, I said a moment ago that you could hydrolyze an ester. And you can hydrolyze an ester in two ways. You can either boil it up with base, like sodium hydroxide, aqueous sodium hydroxide, or you can boil it up with an aqueous acid. Let me first give you the sodium hydroxide route. Let's take an ester. Why don't we take this one, methyl ester, and I'm going to hydrolyze it, which means I'm going to convert it to a carboxylic acid and to ethanol. You know, if it's Christmas Eve and you're in the lab and you're feeling very depressed because nobody has invited you to a party and you're absolutely broke, but you fancy a drink, you could hydrolyze an ethyl ester, isolate the ethanol, and be a little happier. So let's see how this works. If you do this, I'm not encouraging you to do this. You've got to be very, very careful. I don't want you to poison yourself.
Yeah. Give me a try.
And you can see from that series of processes, and I should actually write that they're all. Is that true? That's certainly true. That's true. But the last step's irreversible. If you did this with ethyl acetate, of course you get ethanol and acetic acid, or sodium salt. You add acetate, you get acetic acid, which you could then put on French fries. And I saw, my mother told me this when I phoned her the other day, the Philips electronics company has made a device that apparently, I'm going to look into this carefully, because I'll probably buy it if it's true, makes a device that enables you to prepare French fries without the oil. So you can enjoy the taste without the health
In
problems.
the oven?
That's kind of nice. Apparently they heat the diced up potatoes in very, very hot air, and it produces the same result as deep-fried French fries. I will report on that in due course. Okay, so you know how to hydrolyze an ester by boiling it up with sodium hydroxide. And one thing I draw your attention to, if you would just stop the twittering or whatever it's called. Some of you probably are twittering because I see these wretched little devices in your hands instead of a pencil and pen. One of the things you notice about almost everything that I've told you today is that in almost every case, something with a pair of electrons is attacking a carbonyl group. And the electrons in the double bond move onto the oxygen, and eventually, sometimes picks up a proton, but eventually a pair of electrons comes back and expels a leaving group that was originally attached to the carbonyl carbon. So all of these things, no matter how complicated at first sight they seem to you, they're all the same pattern. They're all the same pattern, but it's just disguised in different ways. And of course, what makes it difficult for you is that each of these different ways is associated with a different compound class, and you've got to remember, oh, this is an ester, this is an acid chloride, this is an amide, and so on. Why you find it difficult to remember, I don't know, because many of you have no problem in memorizing the names of these guys who bash one another over the head with big sticks on a smooth surface that's white and slippery. I think it's called hockey. Okay, I'm going to finish up on a note that's more interesting for all of you. I want to tell you about how to make amides.
I have it in black. Yeah.
What happened to your hair? It's gone.
Oh, I thought this was Sita.
Oh, you're cute, Elle.
Who is she talking to? So sad.
She told me she'd be late. I didn't think she was.
I think she said that she was going to sit up there because she didn't want to disturb her. But
Like my boyfriend was on the worst thing is he has like a November stash.
you don't want to. Stop it. Is that anything?
Here's an amide because
That's her latest thing. That would be like,
Should we all go?
amides are substances of this type, as I've told you before. And what I'd like to ask is, does anybody know what this amide is? No. Well, I'm very pleased that you, normally, if I ask a question you don't know the answer, I'm pretty ticked off. I get upset. But I'm very pleased that none of you know what this amide is, because it means that there are no criminal elements in the audience, because this stuff is a prohibited substance. It's LSD. So if you take, what is that? If you take any of this, you'll get all sorts of, you will start to hallucinate. So this is obviously a famous amide, and its activity was discovered by accident. The person in Switzerland, the medicinal chemist in Switzerland, made some of this, and obviously by accident, a tiny amount got into his mouth. Some was on his hands, he may have touched his mouth, and then as he was cycling home, he experienced all sorts of weird ideas, and it didn't wear off until the next morning. So this is a famous amide, but it still is part of the general class of amides, and I've got time for one quick way of making an amide. I'll tell you how to make this.